Hey guys, I'm Sam. That's my solar powered car, the Sun Eater, and this is a YouTube channel where we look at how to use batteries and solar to extend the range and lifespan of old EVs. But no matter how many extra miles we're able to keep that EV on the road for using our portable solar charging station, eventually that battery is going to degrade to a point where it's really just not suitable for use in an electric vehicle anymore, and it's time to turn those batteries into stationary storage or a Powerwall. Now, in my video, Why Make a Solar Powered Car, I talked a little bit about how when you go out and you buy one of these Leafs for $3,000 or $4,000, you really get a lot of bang for your buck because you don't have to pay for gas for however many years you can get it to last for. And when you get done using it, the battery that's underneath here is perfect for turning into a home Powerwall. There's 48 modules like this, and every one of these Nissan Leafs, and these things go on the aftermarket for around $50 a piece right now. So you're recovering like half the purchase price of the vehicle and the value of batteries. And plus, these modules are, in my opinion, almost perfect for making home power storage for reasons that I'm going to go into in this video today. The first thing we're going to look at is the mechanics of cell size when you're building a home Powerwall. How does using a Leaf module versus the much more common 18650 battery affect the overall build? So let's take a look at the 18650 cell. Probably one of the most commonly produced batteries on Earth. You find them in everything from laptops to electric scooters. This one right here actually is the battery for my headlight that I use, my rechargeable headlight. It's the bread and butter of YouTube channels like Jehu. My buddy Paul Kinnett's built a bunch of Powerwalls out of them. There's several manufacturers of these batteries. The specs for one of the most common producers, Panasonic. Panasonic made all the 18650 cells for Tesla when they first got started. I think in between the years of somewhere around 2011 to 2014, 2015, somewhere in there, Tesla used pretty much all 18650 cells to power all of their electric vehicles that they made. The Panasonic 18650, I wrote some specs down here because I knew I was going to forget them, has a capacity of 12 watt hours. The average used Nissan Leaf module that you're going to find on the aftermarket has a capacity of around 300 watt hours. So in the Powerwall that I'm going to make, I'm going to use 84 of these Nissan Leaf modules. If I wanted, that's around 25 kilowatt hours. If I wanted to get the same capacity in the same 25 kilowatt hour capacity out of these 18650 cells, I would have to use 2,083 of the brand new Panasonic cells with the 12 watt hour capacity. Now, that's the new cell capacity. If you're watching this channel, you're probably not a millionaire, which means you're going to be sourcing these from the aftermarket, getting a bunch of used cells that have slightly less capacity, because they're still a lot cheaper per kilowatt hour overall. You'll get the batteries for 60% off the price new, but they'll have lost anywhere from a quarter to a third of their capacity. So that 2,083 figure that we got for new batteries is probably going to be closer to 2,500, maybe even 3,000 of these things if you wanted to build a 25 kilowatt hour usable capacity Powerwall. So other than just being a very large number, why is that a problem? Well, because when you go to connect all the little strings of batteries, these 18650 cells, to build very large batteries, you have to go spot weld little strips of metal from cell to cell. I'll see if I can put in a video here. I know Zach and Jesse built their own lawnmower battery out of 18650 cells. I'll see if I can splice that in here. And you have to go cell to cell and weld these little tabbing wires on each battery in the series. And you actually have to do it on the top and bottom of the battery. So if you're using anywhere in between 2100 to 2600 of these cells, multiply that by 2, and that's how many of these little connections you have to make. And it is imperative that every one of those connections be solid. When electricity flows from one surface to another, if you've got a really good contact area, the power is going to flow, the current's going to flow easily from one conductive material into the other, and you're not going to get a lot of heat up of that material. If, however, you've got a very weak connection, when you're welding on those little tabbing wires for your 18650 cells, and you don't get one of those connections on real solids where it's just a real thin connection, that current kind of bottlenecks through that thin connection. It can heat up the wire and cause a lot of problems for that Powerwall, if not a fire. So the fewer connections you have to make, the easier and really safer the build is. Which is not to say that you can't build safe battery packs out of 18650 cells. Plenty of people have done it. I have a lot of respect for Jehu, Paul Kennett, the other guys that have done it. They've done it well, but there is an inherent risk in making thousands and thousands of electrical connections in a Powerwall, which is one of the reasons after the 18650 cell, Tesla migrated to the 2170, which is, here, I'll hold this a little closer to the camera so you can see, just a slightly larger version of the 18650. Now, these have, this one right here I got from Samsung. It has a capacity of 18 watt hours, and if I were going to make my 25 kilowatt hour Powerwall out of the 2170 cells, I would be looking at about 1,389 of them brand new. Once again, I would never buy that many brand new because you're going to pay way more per kilowatt hour than you would getting them used. But if you get them used, they have a slightly lower capacity, so you're using more. So that 1389 figure is probably going to wind up being around 1,400 of these cells to build the 25 kilowatt hour Powerwall if I was getting them used. Now, 1,400 times 2, that would be 2,800 electrical connections I would make, because you're connecting on the top and bottom of every cell. And 2,800 connections is still a lot. There's a lot of room to make a mistake in there and leave a weak connection in your Powerwall, which is going to be somewhere where that current bottlenecks through a very thin connection and heat builds up, causing problems. The manufacturing difficulties inherent in building large battery packs out of thousands of cells using multiple thousands of connections is one of the reasons why Tesla's next battery move was to actually manufacture its own cell, the 4680 cell. These are not the actual dimensions of it. It's a little smaller than this. Sandy Monroe did a real good mock-up of what a battery pack would look like using 4680 cells. I'll see if I can put a picture of that up on screen here. But the 4680 cell is going to reduce the total number of cells that need to be in a Tesla car from thousands to hundreds, and it's going to simplify the manufacturing process, and it's going to make the battery inherently safer because there's fewer electrical connections, fewer places to fail. Tastes like future Cybertruck batteries. So, size matters when you're selecting cells to build your Powerwall out of, because the smaller the cells you're using, the more connections there's going to be, the more time consuming it's going to be to make sure all those connections are right, and there's just more room for error. The Leaf battery modules, in addition to requiring far few cells or modules per Powerwall, come with real nice thick copper connections and threaded inserts for your screws as well, so it's a lot easier to get a much more secure connection by threading a bolt in here through a bus bar than it is to run some tabbing wire over an 18650 cell, use your little spot welder and try and nail it just right on every single connection. Once again, it is possible to safely tab thousands and thousands of these cells together. Lots of people do it, but I think for most people, these threaded inserts on the Leaf module will just be a lot easier to get a good, solid, permanent connection on. Okay, so that's it for the mechanics of cell size. Let's take a look at the actual chemistry of these batteries and see if there's any advantages or disadvantages to using Leaf modules versus more traditionally available cells that way. Well, when Tesla started building their electric vehicles out of the 18650 cell, they used this cell because the chemistry has a very high energy density. Most of these are lithium cobalt oxide, which is a very energy dense but also very reactive chemistry. It has lower tolerances to things like heavy discharge rates and over temperature parameters than some other chemistries. But that was a compromise they kind of went with because they needed the energy density in these cars. They needed them to have a range that was going to make them commercially viable. When the Leaf went with the more stable lithium manganese oxide chemistry, it was probably motivated by a little bit of kind of fear, honestly, wanting to stay away from those more volatile chemistries, and the fact that they didn't want to engineer a cooling system for their batteries. That was obviously a terrible idea, but it did pump the aftermarket full of countless tens of thousands of these modules that are made out of the lithium manganese oxide, which is after lithium iron phosphate, I think just about the safest, most stable battery chemistry on the market, which makes these modules great for DIYers, especially DIYers. If this is like your first Powerwall build, like it'll be for me, it just feels better to go with about the least reactive, least volatile chemistry out there. Okay, so that's it for considerations regarding the actual chemistry inside the various batteries. Let's take a look at the voltage ranges of our Powerwalls and what kind of voltage we're shooting for and how we're going to get that. I'm going to get my multimeter and take readings of these three cells, and we're going to see what the voltage is of all three of these batteries. And if you don't know anything about lithium batteries, it'll be I think this will be kind of interesting. If not, you skip to this time in the video and skip past this little section here. So first, let's test our 18650. Right here, we've got 3.9 volts, 3.5 volts for the 2170. And finally, the Leaf module, 3.7 volts on the Leaf module. So that's interesting. We've got 3.7, 3.9, 3.8, somewhere right around there for all three of the batteries. So why is that? Do manufacturers just inherently enjoy making 4-volt battery cells? Our inverter equipment certainly doesn't run off anything that's 4 volts. My inverter that I've got in the Sun Eater is a 12-volt inverter, and all the other inverters are multiples of 12 volts. 24-volt inverter, 36-volt inverter, 48-volt inverters, all being the commonly available sizes for small projects like the type that me and you are going to get into. So, how do we make a battery pack out of 3 to 4 volt batteries that's going to be able to run a 12 to 48 volt inverter? Well, we do that by connecting them in series, taking the positive terminal of one battery, connecting it to the negative terminal of another, adds the voltages of the two batteries. So when I run my 18650 and 2170 in series, well, now I'm up to 7.26 volts. So when we put two of these batteries in series, we double the voltage. If we were to put 4 of them in series, so positive to negative 4 times in a row, you would get a 4S battery. The individual voltage range of these batteries, a good healthy operating range is about 3.2 volts to 4.2 volts per individual battery. So if you stack all 4 of those up and add them together, you get a voltage range that when all 4 of them are fully discharged is 4 times 3.2, or about 12.8 volts, and when they are all fully charged at 4.4 volts each, your maximum voltage of all 4 gets to be 16.8. So a 4S battery made out of 4 of these things could have a voltage range of about 12.8 to about 16.8 volts, which would actually run our 12 volt inverter Fairly well. That's the fully charged voltage of 16.8 would be a little above the parameters of what a 12 volt inverter is operating perfectly at, but it's doable. But what if we wanted to make a 48 volt system, which is going to have a lot of advantages over a 12 volt system that we'll go into here in a little bit? Well, to build a 48 volt battery or Powerwall, we would need 14 of these lithium batteries connected in series. That's going to give us, once again, 14 times 3.2 being the lowest voltage and 14 times 4.2 being the highest voltage, is going to give us a voltage range of 44.8 volts to 58.8 volts. The 48 volt inverters that we can get are going to run very well over that maximum to minimum charge spectrum of our batteries. A 48 volt system also has the advantage, we're probably, if you're building one of these, you're probably going to be charging your battery off of solar. And since most Powerwalls go in people's garages and most solar is going to go, like mine is going to go over the gardens over there, I'm going to build an agrivoltaic system. Well, we're having to move this power 50, 60, 70, 100 feet or more from where the solar is to the batteries. And the higher the voltage you transmit the power at, the less of it you lose to kind of internal resistance in the wiring. And there's pretty cool voltage drop calculators you can find online. I'll include a link in the video description, and I'll see if I can put two shots up on screen here. One of how much power you would lose transmitting 12 volt power through a 100 volt line to your Powerwall, and another one how much power you would lose using a 48 volt system transmitting that power to your Powerwall. Then you can really see that a 48 volt system just has a lot of efficiency advantages over a 12 volt system, and it's still a low enough voltage where you might get where you'll probably get shocked if you touch the two terminals of it, but it's not like a super dangerous voltage to work around. One last point on voltage ranges before we move on. These Nissan Leaf battery modules are actually 2S modules. There's two modules that are connected, two modules in parallel from here to here, and those two are connected to another two modules in series from here to here. So if you test it, these terminals right here, you'll get a range of about 3.2 to 4.4 over the discharge cycle. And if you test here, you'll get twice that, or about 6.4 to 8.4 volts over a healthy charge discharge cycle, where you're not pushing the parameters of what this battery can hold too much, not overcharging it or over discharging it. All right, now on to the importance of balancing all the groups of cells you're going to be using in your Powerwall. You can build a 48 volt battery out of just 7 of these Leaf modules. 7 of these connected in series will get you up to 48 volts. But that battery is only going to have around 7 times 0.3 kilowatts, is a little over 2 kilowatt hours in that battery pack, which is a great battery if you're running like little power tools for short duration. But if you're building a big Powerwall for your home, you're probably going to want something with a lot more capacity than that. So the way to do that is, instead of connecting the positive and negative of this battery to the positive and negative of the next one, I would put 2 of these in parallel and connect the 2 positives and the 2 negatives, and connect that brick of 2 to the next brick that I'm going to flip over, so the positive of this 2 battery group connects to the negative of the next 2 battery group, and basically you double the number of modules you're using. So you're still building a 48 volt battery, but now instead of building it out of 7 modules, you're building it out of 14, and you double the capacity of them. I'm building my Powerwall out of 84 of these modules, so that's going to be 7 groups of 12 modules. And when you start building real large groups of batteries like that, it starts becoming critically important to know the capacity of these individual modules and making sure that your groups have roughly equal capacities, all 7 of them. Well, why is that, you might ask? Why is it so important to make sure that all of our groups of batteries have roughly similar capacity? They're all going into one Powerwall, right? Well, I built a little prop to help illustrate this point that I'm gonna go get right now. So what the heck is this right here? Well, this is a 4S or 4 battery in series lithium battery that I built. You've got 1, 2, 3, 4 of those little 3-volt lithium batteries in series right here, where this would be the overall negative of the battery and this would be the overall positive. I've intentionally, now I know the capacity of each of these modules. I tested like 40 of these things already, and I picked out 3 that I knew had the exact same capacity and charged them all to full, so I could illustrate to you guys the importance of balancing the batteries that goes into your group. So we've got 2 groups here. These 2 are one group, and this is the second group. And it doesn't matter really. You can build these Powerwalls any size you want to. It is in multiples of 7 modules. You can build Powerwalls that have 7 leaf modules, 14, 21, 28, etc., out to hundreds of them if you want. So these groups right here, it doesn't matter how many batteries really are in these groups. This is just illustrating what happens over a discharge cycle of your Powerwall that you're building if you have one of those groups that has twice the capacity of another one of those groups because you didn't test them beforehand and you just threw them all together in the Powerwall. So what I'm going to do is I'm going to hook one of my battery discharge devices up to the positive terminal and the negative terminal of this thing. I'm going to run it for about 0.6 kilowatt hours. I'm going to pull about 0.6 kilowatt hours of power out of this. And then we're going to go back and we're going to look and see how the voltages of these 3 cells compare. They all have the same capacity and they all started at the exact same charge. So in a perfect world, as we discharge this pack right here, well, when I check my battery discharger, after taking 0.6 kilowatts out of this, all 3 of these modules still have the same charge. So I'm going to run that test, splice that footage back into the video right here. This is my little Leaf battery module testing assembly line that I've got set up in here. We've got our 3 module contraption hooked up to the battery discharger, and I actually ran a little past the 600 watt hours I was looking to take out of it. Took 717 watt hours out of these 3 batteries here. So let's take our multimeter and test the voltages of these 3 modules and see if they discharged evenly. On the back module, we've got 7.88 volts, and on this middle one too, it still stays at 7.88. But when we jump to the second group here and test that, that's all the way down at 6.36 volts. That's 6.36 is actually a little below the bottom kind of healthy discharge threshold of these modules, which is around 6.4 volts. So why did so much more power come out of this one than came out of those 2? That's because when you discharge a group of batteries in series, the same amount of power tends to come out of each group. And so if one group has a lot more capacity than another group, you're going to wind up over discharging the weakest group in your Powerwall and potentially damaging those cells. So that's why you have to test all of your cells that are going to be in your Powerwall beforehand and arrange those into groups that have roughly equal capacity. And this is actually another requirement that makes the Leaf module shine, is because we talked about earlier how you would need thousands of these guys to build a Powerwall. Well, that also means that you have to test thousands of 18650 or 2170 cells to make sure that all those groups are equal. While testing all these Leaf modules is a pain in the butt, I only have to worry about testing a lot fewer modules if you're using big battery cells than it is if you're using little tiny ones. And that's one more feature that really makes these Leaf modules shine when you're building a Powerwall out of them. Okay, one more detail before we move on. Sorry this is turning out to be such a technical, detail-heavy, and somewhat boring video. I'm sure a few of you guys are asleep already. But whenever you build a big battery like this, you attach a BMS to it. And some people may be thinking, well, who cares if my groups get a little bit out of balance? The BMS is there to adjust these groups as needed and keep their voltage even. But the BMS is really designed for kind of fine, minute adjustments. I'll put a picture up on screen here of the BMS that I'm using, the 48 volt BMS that I'm going to use for my Powerwall. And the wires that run to these individual groups of batteries are very thin. They're not designed to move large amounts of current. They're designed to just make small little fine adjustments. And if you're pulling a lot of power out of these Powerwall, and a few of your groups have very different capacities, the BMS will not be able to keep up. So even with a BMS, it is important to ensure that your groups have even capacity. Okay, on to the next section. One more point to consider when building your home Powerwall is thermal management. These batteries, regardless of which cell type you choose to go with, have to operate within regulated temperatures. You don't want to operate any of these at like 100 degrees Fahrenheit or well below freezing. Obviously, as we've learned from Nissan Leafs, these modules like to be kept cool as well. Somewhere in between 60 and 70 degrees is probably what I would shoot for. We've seen the amount of miles that these battery packs are able to drive these Leafs vary from as little as like 40,000 miles in Arizona to upwards of, I think it's like 180,000, almost 200,000 miles in northern parts of Europe, where it stays very cold all the time. And that indicates, what that tells us as we're building our Powerwall is, what's 180 divided by 30? That's almost a 6x, 6 times as many cycles that you can get out of these batteries when they're kept at cooler temperatures in that kind of 50 to 70 degree range. We're going to invest a lot of money in building these Powerwalls, building these backup power supply stations for our house, for charging our electric vehicles, backup power for the house, whatever it may be. We're going to invest a lot into it, and we want to make that investment last. So it's going to be critical to regulate that battery temperature. Now, these Leaf modules come with handy dandy little holes punched in all the corners there that you can run these rods through. And if you live somewhere where it's very cold a lot of the time, then you're probably going to want to cinch these batteries right up next to each other so that they kind of heat each other as they charge and discharge. Really pack them in together. But if, like me, you live somewhere where it stays warm all the time, you're going to want to get as much airflow in between these batteries as possible. When we are stringing our batteries along our guide rod here, we can go through and put little rubber spacers in there, and that's going to allow for some airflow to travel in between these modules when we've got dozens and dozens of them, as we will in a home Powerwall situation. The shelving problem is not a really hard one to solve. Metal shelves come in every shape and size, and a lot of them have basically just the shelves are just little bars. It's a little rack of bars, and that's going to be perfect for us because it's going to, once again, allow airflow to travel over all those batteries. So the way I plan on building my Powerwall is that the bottom 2 or 3 shelves will be just modules, and I'm going to save some room on that very top shelf to install an air conditioning unit. And it doesn't matter what kind of air conditioning unit you use. You can use a little window unit, like people mount in their windows. You can do a split unit, which is what I'm going to try and do, where the evaporator is on the inside of your little server box that's going to contain your Powerwall, and the compressor is going to be somewhere outside of the garage. But by doing that, by using one of these metal shelves, we should be able to put dozens of these things in a compact, easy to insulate, easy to cool footprint that's not going to take up a whole lot of space in your garage, and should last, if we space them out so that they can breathe a little bit, should last us years and years. Okay, now onto the price consideration. these modules, if you don't have you want to build a Powerwall out of a Leaf, but you don't have one, an old one that you're going to drop the battery pack out of, you used to be able to find full Leaf battery packs on eBay for right around $1,000 a piece. Now these had 10 kilowatts worth of modules in them at the worst, usually, and you could get 10 kilowatts of batteries for $1,000, which is right around $100 a kilowatt hour. That was an outstanding price. When I made my video on the solar trailer Leaf giveaway that I wanted to do, one of the ways I was going to build that was using these dirt cheap aftermarket batteries. But something happened recently. I made a post on my Patreon page about this. Somebody has been buying hundreds of thousands of these things off the aftermarket, cleaning the aftermarket out, driving up the price, and you're coming in closer. Instead of 100 kilowatt hours, now you're getting them for closer to 130, which isn't quite the just screaming deal that it used to be, but $130 a kilowatt hour for a Powerwall is still a pretty good price, especially considering all the things that these modules have to offer. Stable chemistry, easy, strong connections. You don't have to sit there and spot weld, the little tab wire on 100 different spots, and larger cell size, so that you don't have to sit there and test, 3,000 individual cells like you would with this. $130 a kilowatt hour for all of that in one package, I think is a really good option for first-time Powerwall builders like myself. And while we're on the subject of price, a story came out a couple months ago that I was very excited to see, by Electrek. I'll post the article here, about how Redwood Materials is going to be recycling Nissan, is working on a program to recycle these batteries in the near future. Now, when I build my Powerwall out of 84 of these things, that's hundreds and hundreds of pounds of lithium and manganese, and I think some nickel in there as well, that is in very short supply on the market these days. As the rate that we manufacture electric vehicles and use batteries to back up our power grids accelerates, demand for these supplies, the raw elements that go into these batteries, the demand is growing way faster than we can establish new mines to mine this stuff out of the ground. And that has made the business of recycling these batteries a lot more lucrative. So if you buy this module for $40 today, use it in your Powerwall for 4, 5, 6 years, when you go to sell this thing back to a battery manufacturer, well, 84 of these modules has everything they need, all the raw elements they need to build essentially a brand new battery pack for a Tesla. And these battery packs that go in these Teslas are valued at around $10,000 today. So if we can build our Powerwall out of $2,000 or $3,000 worth of these modules, and the materials in that is worth $10,000 to the manufacturer, the recycler, I think there's a good chance the recycler will be willing to pay us a significant portion of our initial investment, our initial $2,000 to $3,000 investment, allowing us to recoup a lot of the expense of this Powerwall when we go back and pay for these things, when we go back and sell these things to the recycler years from now. And I was very excited to see that Redwood Materials is working on a recycling project for these modules. That's great news for me, and great news for anybody else out there who's planning on building a Powerwall out of these things and might want to sell it to a recycler years from now. Okay, that's all I got. That's all my considerations on using the Leaf module to build a Powerwall of your own. As these things have gone up in price, I don't have the cash to buy all these modules offline that I was going to use to build my Powerwall, so I'm just going to drop the battery out of the Sun Eater, break that open. It's got 48 of those modules in there. Combine those with the ones I bought offline to get up to the 84 total count that I need to build my Powerwall. And then I'm going to take the good battery, the 10 bar battery, out of that black Leaf over there, put it into the Sun Eater, and that should keep my solar car on the road for years to come and give me all the batteries that I need for my Powerwall. And then we've got a backup car that I can use to kind of do wiring and install experiments with, because when you're doing experiments on the car that you're relying on to get you to work, it's kind of nerve-wracking. So I'm very glad that I'll have a parts car. I'm gonna use the tires off of it. The windshield on this one's cracked, so I'll pull the windshield off that one. Everything in this car is getting reused. Nothing's getting thrown away. And I get a new battery in my daily driver, and I get batteries for my Powerwall. It wound up being a real home run, considering these vehicles cost me $3,000 and $3,900 respectively, and I can sell that Powerwall back, and I haven't had to buy gas for years. It's really just a financial home run if you're willing to do a little bit of elbow grease, and I think you'll have a lot of fun with it along the way. I certainly have. Okay, that's all I got for today. Shout out to my patrons who support me over on Patreon and these little experiments and demos that I all build. All these copper bus bars, the 2170 cell. Like, I buy this kind of stuff just to do kind of educational videos for you guys, and it does have a price tag, and my patrons help me offset that so that I can continue to bring you guys these videos. And as a kind of thank you to them, recently I've been allowing my patrons to have a say in the next videos that I produce. So if there's a video that you want to see, or you want to kind of get a little say in the direction that some of these experiments that I'm doing go, for as little as $2 a month on Patreon, you can support me. There will be a link in the video description, and then you can say, hey Sam, do this crazy thing or that crazy thing next. All right, that's all I got for today. Thank you guys. I'll see you next time.